Greetings, members, one and all of the Salivation Nation. Strange metal, strange behavior. Let's explore! For those of you familiar with this channel's history, you know that I like to cover all kinds of metal. That's right. Mostly it's about precious metals, but I've done videos on many different types of metals, and this is the first. It's a very strange metal that has been discovered. This is the only known image that I could find, and this is a story that was sent to me by Freedom Stacker. If you enjoy videos like this where I talk about various different topics related to metals, I hope you will consider subscribing, maybe pressing that thumbs up button, as well as engaging in the comment section and pressing the notification bell so that you can be apprised of the latest content that makes its way across your device. This is from The Independent. Scientists find a strange metal that behaves in ways they don't quite understand, and that is a discovery that could be key to finding out an explanation for a phenomenon that has troubled researchers for decades. Solving that problem could lead to a variety of breakthroughs, such as lossless power grids and quantum computers. It also appears to be linked to some of the fundamental constraints of the universe, or constants of the universe, so could help shed light on how the cosmos actually works. You know, discoveries like this in science are quite intriguing, and metals play an important role. Now, we know that most materials, such as copper and silver, behave in very predictable and well understood ways. Scientists understand how their electrical conductance changes when they're heated and cooled. But recently, scientists have focused on another class of materials known as strange metals. They do not seem to behave according to the usual electrical rules. Scientists are doubly intrigued because they are thought to offer hints of the quantum world, as well as a way of understanding other phenomena that is yet to be fully explained. Scientists have found another strange metal behavior and another mystery to be solved. In the material, electrical charge is not carried by electrons as usual, but by so-called Cooper pairs that are more like waves. We can kind of see in some way there, we can see how this is dynamically put out here, shown in this image. Fascinating indeed. Electrons are part of a class of particles called fermions, and Cooper pairs are bosons that behave very differently. Strange metal behavior has never been seen in a system with bosons. We'll look at that more closer with a more detailed article here in a moment. It could help finally solve the decades-long mystery of why this strange metal behavior actually happens. We have these two fundamentally different types of particles whose behaviors converge around a mystery, said Jim Valles, professor of physics at Brown and an author on the new study. What this says is that any theory to explain strange metal behavior can't be specific to either type of particle. It needs to be more fundamental than that. So the research is called Signatures of a Strange Metal in a Bosonic System, published in Nature. Now, I looked, and there was limited access to that article. Largely, it's very, very detailed, and you probably get too much into the weeds with that. We're going to look at another article here momentarily. It might give us some further insight, but we don't want to get too much into the weeds on this, because obviously there's a lot of technical science involved. But nonetheless, this behavior has been puzzling scientists for 30 years. So they've known about these strange metals for quite some time. Since a class of materials called cuprates was discovered not to act like other metals. When normal metals were heated, the resistance goes up until a certain point when high temperatures mean the resistance becomes constant, but in curates that doesn't happen, and the strange metals refuse to obey the expected rules. Researchers don't know why that might happen, but they do know that it appears to be linked with two different constants, one that relates to the energy produced by thermal motion, and Planck's constant, which relates to the energy of a particle of light. To try and understand what's happening in these strange metals, people have applied mathematical approaches similar to those used to understand black holes, Vallée said. So there's some very fundamental physics happening in these materials. So to better understand what's happening, scientists used a cuprate material that had tiny holes in it to produce copper pairs. They cooled it down and watched how its conductance changes and found that it was behaving like fermionic strange metals. This does not explain where the strange behavior is coming from, but it does give a new piece of information for them to try and understand it better. It's been challenging. Let me stop this. It's been challenging for theoreticians to come up with an explanation for what we see in strange metals, Vallée said. Our work shows that if you're going to model charge transport in strange metals, that model must apply to both fermions and bosons, even though these type of particles follow fundamentally different rules. And if you look over here, this article here gives a little bit more of an explanation that it was from this physicist from China and the U.S. that detected this unexpected signatures of strange metallicity in a material in which electrical charge is carried not by electrons but more wave-like entities called Cooper pairs. And there's that image. And it was first discovered around 30 years ago in these cuprates that we talked about. And the copper oxide materials are most famous for being high temperature superconductors, meaning they conduct electricity with zero resistance at temperatures far above that of normal superconductors. And this could be very helpful down the road for applications. But even at temperatures above the critical temperature for superconductivity, cuprates act strangely. As their temperature increases, cuprates' resistance increases in a strictly linear fashion. So in normal metals, the resistance increases only so far, becoming constant at high temperatures in accord with what's known as Fermi liquid theory. Resistance arises when electrons flowing in a metal bang into the metal's vibrating atomic structure, causing them to scatter. Fermi liquid theory sets a maximum rate at which electron scattering can occur, but strange metals don't follow that Fermi liquid rules, and no one is sure exactly how they work. What physicists do know is that the temperature-resistance relationship in strange metals appears to be related to two fundamental constants of nature. Boltzmann's constant, which represents the energy produced by random thermal motion, and Planck's constant, which relates to the energy of a photon. So to try to understand what's happening in these strange metals, people have applied mathematical approaches similar to those used to understand black holes, as the other article said from Dr. Valles. So there are some fundamental physics happening there. And in 1952, Leon Cooper discovered that in normal superconductors, electrons team up to form these Cooper pairs, which can glide through an atomic lattice with no resistance. Despite being formed by two electrons, which are fermions, Cooper pairs can act as bosons. Fermion and boson systems usually behave very differently, unlike individual fermions, bosons which are allowed to share the same quantum state, which means they can move more collectively, like water molecules in the ripples of a wave, according to Dr. Valles. In 2019, the researchers showed that Cooper pair bosons can produce metallic behavior, meaning they can conduct electricity with some amount of resistance. That in itself is a surprising finding because elements of quantum theory suggested that the phenomenon shouldn't be possible. For the latest research, the scientists wanted to see if bosonic Cooper pair metals were also strange metals. They used a Cooper material called Ethereum barium copper oxide patterned with tiny holes that induced the Cooper pair metallic state. And I think that's kind of what we're seeing in that image above here, is that there it is. Very interesting indeed. That's yttrium, barium, copper. Then they took the materials down to just above its superconducting temperature to observe changes in its conductance. They found, like fermionic strange metals, a Cooper pair metal conductive that is linear with temperature. It's been a challenge for theoreticians to come up with an explanation for what we see in strange metals. Our work shows that if you're going to model charge transport in strange metals, that model must apply to both fermions and bosons, even though these type of particles allow fundamentally different rules. So it's interesting, fascinating discovery here. I think we're quite a ways off before any kind of application, because obviously still in the stage of understanding the physics behind this. But what an amazing story, how this works. And it's pretty amazing how different kinds of metals have been around for quite some time that have been strange, and they made this new discovery and discovered this strange behavior with them. Nonetheless, metals are part of our lives in every way, shape, or form. And I think a story like this, as again, I want to thank Freedom Stacker for sharing this with me, is quite a good reason why this channel is called Salivate Metal as opposed to being tied to any particular metal. Because I believe that in all the metals, I think they're all neat and unique in their own special way. And even the strange metals in a strange land with strange behavior. And that is the case here. So an interesting article here on the science in metals. Let me know what your thoughts are in the comment section below. I would like to extend a multitude of gratitude to you all for taking the time to watch, and to encourage you to please rate, share, comment, and subscribe.